Hello and welcome. This is the second video in Newtonian gravity video series. And last time I stopped at this billiard ball problem. So on a pool table, I have to Google some numbers here. A typical pool table, which is just a rectangular block. And so the dimensions, let's write down the dimensions. Let's call it D. This is 37.25, 37.25 inches long. Let's convert this to meters. So 1 inch is 0.0254 meters. And let's see, 37.25 times 0.0254. It's about 0.946, let's say 0.95 meters. 0.95 meters. And the other dimension, let's call it L. This is 74.25, so 74.25 times 0.0254. This is 1 meter and 89 centimeters. 1.89 meters. Okay, and I'm using 3 balls, one here, another one here, and one over there. These are 0.16 kilograms each. Now, the goal is to find the force on this one, and after that, let's find the force on the one in the other corner. Okay, so on this guy here, I have a force vector that points to the right. That's because of this ball. And the other one here, which is at 90 degrees to the first one. Let's call these F1 and F2. Okay, so once I get this done, meaning what is the sum of F2 and F1. I'm going to add them in a vector fashion. I can calculate the force on the other one. Let's say this is number 1. Well, let's call it A. This is ball A, and then this is ball B. What will be the net force on ball B? Okay, and I'm totally ignoring their weight. So. All right, so let's start with the sum of F2 and F1, which will be, complete this to a rectangle. It's in this general direction, okay? It looks like 45 degrees, but it doesn't have to be, of course. It depends on, you'll see in the values of F2 and F1, but this will be the sum. So this will be F1 plus F2. So let's find it. Let's find the magnitude of F1 and F2 first, and then do the vector addition. So we're going to use the formula for Newton's universal gravitation. Fg is equal to this constant times the first mass times the second mass, divided by the square of the distance between them, distance measured from the centers of the objects. Now, that distance for A and B may not be exactly 0.95, but let's ignore that for a moment, okay? Let's just use this number for our separation for A and B. Okay, so F1 then let's find F1. The magnitude of F1. We'll need G, that's 6.67 times 10 to the negative 11 kilogram meters squared. I'm sorry, Newton meter squared per kilogram squared. Now this times MA times MB, which are both 0.16 kilograms. So I'll need here 0.16 kilograms squared. In the denominator, I'll have D, which is 0.95 meter squared. Okay, so 6.67, 10 to the negative 11 times 0.16 squared divided by 0.95 squared. And that is 1.89 times 10 to the power negative 12 newtons. Very small number, okay? Now compare this to the weight of the ball. Compare this to the weight of the ball, which will be m times g, right? G is 9.8, so 9.8 times 0.16. The actual weight is about 1.57 568 newtons. That's how large compared to these forces we are dealing with. But it's okay. That's F1. Now remember, that's the force ball B attracting ball A with. Similarly, ball A will attract ball B with exact same force, only in the other direction, of course. So let's repeat this for F2. The magnitude of F2, 6.67 times 10 to the negative 11 times 0.16, and the 1.89 is the length. Both are squared. So 0.16 divided by 1.89. Take the square of this number and then multiply by 6.67, 10 to the negative 11. All right, so this will be 4.78 times 10 to the negative 13 newtons. All right, so let's take this one and rewrite it as 18.9 times 10 to the negative 13 newtons. All right, then we need the vector sum. Now these two are perpendicular to each other, so they act like the x and y components of the net force. So F1 and F2, when added, will have a magnitude of 18.9 times 10 to the negative 13 Newton squared plus 4.78 times 10 to the negative 13 Newton squared. And then take the square root of that. (18.9) squared plus 4.78 squared take the square root times square root negative 26. So what I got is 19.5 19.5 newtons. All right, that's the net force, or the force along the xy plane, in this case the pool table. On ball A. Due to balls A, due to balls B and C. Let's call it C. Now let's repeat the calculation, but now repeat for ball B. Now we already have half of the answer, so just need to copy that, right? So let's mark the forces first on B. Let me use green. And then B will also be attracted towards this direction, in this direction, towards C. I'm going to call it F3. And this is equal in magnitude, equal to F1. So do you mind if I just call it F1 again? All right, so F1, we found F1. That was 18.9 times 10 to the negative 13 newtons. What is F3? All right. Now to find F3, I need to know R for balls C and B. Okay, so we're talking about the hypotenuse there. What is this? What is that? So that will be square root of 0.95 squared plus 1.89 squared. I need the square of R anyways, but let me just find what the actual distance is. 0.95 squared plus 1.89 squared, and take the square root. 2.12. So this is 2.12 meters. All right, so what is F3? F3 will be 6.67 times 10 to the negative 11. Not writing units to save time. And 0.16 squared divided by 2.12 squared. So 6.67, 10 to the negative 11 times 0.16 squared divided by 2.12 squared. So this is 3.799, 3.8, 3.8 times 10 to the negative 13 again. Newtons. Okay, so the force on B due to C is 3.8, and the force on A due to C is 4.78. So the numbers are consistent. Okay, so let's find the net force on B. So here's B. We have what I called F3, and then here is F1. So the sum will be in this direction. That is your net force. So I will have an angle here, theta, and this, let's call it phi. All right, so I'll need those when I add them. Now, F1 and F3, let's call the sum just F. So F will have an x component. Okay. I'm just writing the magnitude of it. It's pointing to the left, so it's a negative number, but don't worry about it right now. So basically we'll have F1, which is 18.9 times 10 to the negative 13. So 18.9 times 10 to the negative 13 newtons. In the same direction, I will have the horizontal component of F3, which I will find after multiplying F3 by sine of phi. So 3.8 times 10 to the negative 13 newtons times sine phi, which will be 0.95 divided by 0.95 divided by hypotenuse, which is 212, 2.12. So 0.95 divided by 2.12, 0.448, that's sine. So almost less than 30 degrees times 3.8, 10 to the negative 13, plus 18.9, 10 to the negative 13. So this is 20.6 times 10 to the negative 13 newtons. Fy, F is the sum of F1 and F3. The sum, net force, ignoring the weight, of course, Not force. Fy will be f3 times cosine phi. So 3.8 times 10 to the negative 13 newtons. Cosine will be 1.89 divided by 2.12. 3.39 times 10 to the negative 13 newtons. Okay, so now that I have these two, F on B due to A and C, the square root of 20.6 squared plus 3.39 squared times 10 to the negative 13 newtons. So 20.6 squared plus 3.39 squared. Take the square root, 20.88, 20.9, let's say, 20.9 times 10 to the negative 13 newtons. Okay, so all right, that's the force on B. What will be the force on C? Same way, you can just work it out. Okay, so let's do one more. What about really large objects like the moon, the earth, and the sun? So I Googled some numbers here about the dimensions of the earth, moon, sun system, and the masses and etc. So let's copy this data sheet here, copy, and then open up another whiteboard, unsave changes. It's okay. Create new whiteboard. Just delete this. Create new whiteboard. Copy. Control. All right. So, okay. So what to do with these now? All right. Here's the sun. All right, the sun. And here's the earth. Now the earth is in orbit around the sun. And around the earth, we have our moon. So I'm going to consider first when the moon is right here between earth and the sun, and then here on the opposite side. This is our moon. Now when the moon is right between the sun and the earth, it blocks the sun for some time. That's when a solar eclipse happens, right? A solar eclipse. And then when the moon is here, the shadow of Earth is on the moon. That's when we have the eclipse of the moon, or lunar eclipse. Lunar eclipse. Okay, so let's find the force on the moon at these instances when we have these two eclipses. Okay, what is the force on the moon? So, and we're ignoring other planets and galaxies, I mean everything, just these three that we have to take into account. So the moon will be attracted towards the sun, of course. Let's call it Fs. But on the other hand, Earth is also attracting the moon, Fe. All right. So what will be the vector sum of these two, Fs plus Fe? All right, for the solar eclipse. And then we can repeat for the lunar eclipse. When the moon is on the other side, the forces, these forces are in this direction. That's Fe, also Fs. Okay. How do you add these? All right. So let's start with the solar eclipse. We'll need the formula for the gravitational attraction. Let me just copy it here. Fg is G times Ma Mb. Just following the previous problem's notation over R squared. All right, so R for this problem, we need the moon-sun distance and we need the moon-earth distance, the distance between the Earth and the moon. Now that is actually really small compared to the Earth-sun distance. So where are those numbers? Right here. We have this number here, and then this. All right. Let me quickly check something here. So 92,955. 7 times 1, 49, 597, 8, 7, divided by 92, 955,807. Okay, so numbers check. Okay, so let's find this force. Let's apply it to moon. Now this vector sum here, we got to be careful because these two vectors point in the opposite directions. So we got to subtract one from the other. Basically, that's what we need to do. But let's find the magnitudes first. So this force will be 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the sun's mass, that is 1.988, so 1.99 times 10 to the power 30 kilograms times the moon's mass. Where is it? 7.35 times 10 to the power 22 kilograms. All right, and For R, we need the distance between the sun and the moon. Now, you could take it approximately equal to the distance between sun and the earth without any trouble. But for now, let me just write it explicitly. So I'm going to take the distance between the earth and the sun, which is 149 million kilometers. So 149, million kilometers, 10 to the 6, that's million. Convert to meters, that's billion. And subtract from this the distance between the Earth and the moon this year. Let's call it capital R. That is 238,855 miles, and 1 mile is 1609 meters. So 1609 times 238,855. That is 384. 10 to the 6. Okay, I mean, you see there's orders of magnitude, 1,000 times greater, so meters. So by subtracting this number from that, I'm not really achieving a lot. I could take it simply equal to 149 without too much trouble. 384 times 10 to the, or let me just put 0.3 here. How about that? And this will be 9. And then I'll square it. Okay, there's a dot here, 0.834. Okay, so let's find this. For 1 to the power 9. Square that. Take the reciprocal of that. Times 1.99. 10 to the power 30. Times 7.35. 10 to the power 22. Times 6.67. 10 to the power -11. So the answer is 4.417, 4.42, 4.42 times 10 to the 20th power in newtons. That's the pull of the sun on the moon. Similarly, Fe 6.67 times 10 to the -11. Okay, the moon's mass was 7.35 times 10 to the 22nd. We need Earth's mass now. That is right there, 5.97 times 10 to the 24th. Okay, 100 times heavier. And what was it? 0.8384 times 10 to the 9 squared. That's R, right? 6.67 10 to the -11 times 7.35 10 to the 22nd times 5.97 10 to the power 24 divided by 384 10 to the 9 squared. So I got 1.9848, so 1.99, let's say, about 1.99 times 10 to the 20 newtons. Okay, so sun is pulling that way, Earth is pulling the other way. So the net force will be towards the sun. Let me show it with green here. The net force will be this way. The net force then will be 4.42 times 10 to the power 20 newtons minus 1.99 times 10 to the 20 newtons. So that is what, 2.43, right? 2.43 times 10 to the power 20 newtons. All right, that's the force on the moon during a solar eclipse. What about the lunar eclipse? I'm not going to go through all that again, because I know that the force on the moon due to the sun will not change that much. So approximately, the net force during lunar eclipse will be this plus that. At least FE will be the same, and FS doesn't change that much. I mean, if you want, just put a plus here and do it again. It'll be very close number there. So pretty much 6.41 times 10 to the 20th newtons. All right. So if you like, just Google these and see how close we got. Okay. So that's that's another application of Newton's universal law of gravity for astronomical size objects. Okay. So I'm going to stop here. In the next video, I'm going to talk about the relation between this G and